All right, I hope everyone's having a good weekend here. So, allow me to ruin that by reading more of this PDF here. So, we've got uh, we're reading the PDF Situational Awareness by Leopold Aschenbrenner. Leopold Aschenbrenner is a very, very bright person. He graduated from uh, Columbia as valedictorian. He works at he used to work at OpenAI on the alignment team. And he was recently on a really good podcast. I recommend everyone subscribe to and watch the Dwarkesh Patel podcast. He was recently on that, and he talked about um, what we're reading now, and it took him 4.5 hours. So I'm really investing some time into listening to him more carefully. I don't think I was able to get through all 4.5 hours of the podcast, but I think this is a better format for really understanding his message is reading what he wrote here. So this is in addition to a PDF, it's also a website. It's situational-awareness.ai. And it describes the decade ahead and how that's going to change with the advancement of AI. And then up to speed with where we're at now, what the to summarize what we've read so far, the advancement of AI is basically like no other advancement we've seen in any other technology. So if you think of how computers have changed, the internet, how that's changed the world, this is going to change the world much more significantly than that, and it's going to happen quick. By 2027, ChatGPT will be so much more advanced than it is now that it'll basically be unrecognizable. And beyond that, the entire world will start to look quite a bit different. But as soon as next year, um, the capabilities of AI are going to uh, continue to grow to the point where um, it might be capable of doing real impactful scientific research. And once it gets to that point, we're going to have all sorts of unsolved mathematical problems solved. We're going to learn everything there is to learn about the right way of doing things. And just imagine what the world would look like now. On the internet, we have people saying studies are wrong, people saying they're right, and people are just really badly misinformed on the internet and are behaving in really erratic ways as a result. So, imagine we have this super intelligence that definitively proves and can explain to anyone because it's so good at understanding psychology and understanding how to talk to people and stuff, that people just start doing the things that they know make sense. People know that when you eat less and exercise, you lose some weight and become healthier. So imagine an AI being able to design a way for people to actually do what they already know they need to and that they want to do, but they just can't. So, and then the other thing to remember is that when it comes to major technological advancements, the order in which the advancements occur matters a lot. So the atom bomb happened a long time ago. The atom bomb was developed as part of World War II, so it was developed in the 1940s. And we are in this kind of game theoretic situation now with the atom bomb, where there is mutually assured destruction, but this is why the development of super intelligence is important as well, because it'll teach us how to handle things like the atom bomb better. And the atom bomb is still continuing to, the technology behind the atom bomb is still continuing to improve. We're able to make more powerful weapons, and the capabilities for harm are growing as well. So it's important that we have the intelligence to handle and mitigate our technology. So that's kind of the good news is that the rate at which the super intelligent explosion is happening, if it's aligned properly, could really save us from some problems later on. So that's kind of some good news that I got from this. But now we're going to dive into really deep, in-depth discussions of the potential bottlenecks to progress in this, and the author's going to say why they're really not bottlenecks. And remember, I've said this a lot. If there is any one bottleneck, anything getting in the way, there are other things that are driving the progress in AI development as well, so that it will continue to look at on whole as if it's progressing, even if there's a major disruption to one of the things that's causing the advancement. All right, so I'm going to make sure I do a more careful sound check now. Good. And let's continue. So if you'd rather skip the in-depth discussions on the various bottlenecks below, click here to skip to the next section. Nope, we're going to dive right into it. All right, so limited compute for experiments. Optional in more depth. The production function for algorithmic progress includes two complementary factors for production: research effort and experiment compute. The millions of automated AI researchers won't have any more compute to run their experiments on than human researchers. Perhaps they'll just be sitting around waiting for their jobs to finish. So that's a good point. The research itself could be a bottleneck. To the point where it doesn't matter how skilled your researcher are. You know, they have to mix the chemical reaction, and maybe the chemical reaction takes 100 hours to complete. Well, if that's the case, it doesn't matter who the researcher is. If it's a measly human researcher, or if it's a fleet of automated super intelligent researchers, you still have to wait that 100 hours for the chemical reaction to happen. This is probably the most important bottleneck to the intelligence explosion. Ultimately, this is a quantitative question. Just how much of a bottleneck is it? On balance, I find it hard to believe that the 100 million Alec Radfords couldn't increase the marginal product of experiments compute by at least 10 times, and thus would still accelerate the pace of progress by 10 times. There's a lot you can do with smaller amounts of compute. The way most AI research works is that you test things out at a small scale and then extrapolate via scaling laws. Many key historical breakthroughs required only a very small amount of compute. For example, the original transformer, GPT-1, was trained on just 8 GPUs for a few days. And note that with around 5 orders of magnitude of baseline scale up in the next 4 years, small scale will mean GPT-4 scale. The automated AI researchers will be able to run 100,000 GPT-4 level experiments on their training cluster in a year, and tens of millions of GPT-3 level experiments. That's a lot of potential breakthrough new architectures they'll be able to test. A lot of the compute goes into larger scale validation of the final pre-training run, making sure you are getting a high enough degree of confidence on marginal efficiency wins for your annual headline product. But if you're racing through the OOMs in the intelligence explosion, you could economize and just focus on the really big wins. As discussed in the previous piece, there are often enormous gains to be had from relatively low compute unhobbling of models. These don't require big pre-training runs. It is highly plausible that the intelligence explosion starts off automated AI research. For example, discovering a way to do and RL, I'm not sure what RL is. On top of that, gives us a couple OOMs via unhobbling wins, and then we're off to the races. So I think let's use ChatGPT to see what RL is. Okay, so okay, good. But now tell me. Oh, I see. Okay, so RL stands for reinforcement learning. So it's a reinforcement learning technique. Okay, that's what I was going to ask you is what RL meant, but it looks like it means reinforcement learning. Yeah. Okay, so that makes sense. So um, it is highly plausible that the uh, intelligence explosion starts off automated AI research, for example, discovering a way to do reinforcement learning on top that gives us a couple OMs via unhobbling wins, and then we're off to the races. So this is like having a human team do some testing on the responses and vote up or down the good or bad responses. You can make the program better just by doing that, and you really don't have to feed in a lot more to the system besides that reinforcement learning. All right, so as the automated AI researchers find efficiencies, that'll let them run more experiments. Recall that near 1,000 times cheaper inference in 2 years for equivalent math performance, and the 10 times general inference gains in the last year, discussed in the previous piece, from mere human algorithmic progress. The first thing the automated AI researchers will do is quickly find similar gains, and in turn, that'll let them run 100 times more experiments on, for example, new reinforcement learning approaches. Or they'll be able to quickly make smaller models with similar performance in relevant domains. CF, previous discussion of Gemini Flash, uh, near 100 times cheaper than GPT-4, which in turn will let them run many more experiments with these smaller models. Again, imagine using these to try different reinforcement learning schemes. So reinforcement learning, you're teaching them. It's like clicker training with a dog. So if you can find a better way than that, that's going to make it a lot better. There are probably other overhangs too. For example, the automated AI researchers might be able to quickly develop much better distributed training schemes to utilize all the inference GPUs, probably at least 10 times more compute right there. More generally, every order of magnitude of training efficiency gains they find will give them an order of magnitude more of effective compute to run experiments on. So I will advance the bookmark here. Okay, and then delete the old one. And now what I will do is, I'm curious what this CF means. So let's just feed this whole thing in. And let's say, what does CF mean? Okay. So there's a point where the author uses parentheses, and okay. So there's a point where the author uses parentheses, and then the first thing in the parentheses is CF. So like, what does the CF mean there? Oh, confer. Okay. All right. It's an academic way of writing. Okay. All right, that makes sense. So CF, so compared to previous discussion of Gemini Flash, so it means confer, yeah, academic way of writing. The automated AI researchers could be way more efficient. It's hard to understate how many fewer experiments you would have to run if you just got it right on the first try. No gnarly bugs, being more selective about exactly what you are running, and so on. Imagine 1,000 automated AI researchers spending a month equivalent checking your code and getting the exact experiment right before you press go. I've asked some AI lab colleagues about this, and they agreed. You should pretty easily be able to save 3 times to 10 times of compute in most projects merely if you could avoid frivolous bugs, get things right on the first try, and only run high value of information experiments. So, like I said before, it doesn't matter if you have a fleet of super intelligent automated researchers. If you're doing an experiment that involves a chemical reaction that takes 100 hours to run. But where you'd get that advantage is if you don't have a super intelligent team of automated researchers. First of all, you might have to run that multiple times. You might not get it right, so you'll have to do it again, and now it'll be 200 hours at least. And then the other thing is you might not have to use that reaction. There might be one that doesn't take as long. And there might be ways to reuse the results instead of having to do it, every time. So even with that bottleneck there, which is the research itself, takes a while. You can save 3 to 10 times the compute on most projects by getting it right the first time, by avoiding frivolous bugs, and by only running high value of information experiments. All right, so the automated AI researchers could have way better intuitions. Recently, I was speaking to an intern at a frontier lab. They said their dominant experience over the past few months was suggesting many improvements, many experiments they wanted to run, and their supervisor, a senior researcher, saying they could already predict the result beforehand, so there was no need. The senior researchers' years of random experiments messing around with the models had honed their intuitions about what ideas would work or not. Similarly, it seems like our AI systems could easily get superhuman intuitions about ML experiments. They will have read the entire machine learning literature and be able to learn from every other experiment result and think deeply about it. They could easily be trained to predict the outcome of millions of machine learning experiments and so on. And maybe one of the first things they do is build up a strong basic science of predicting if this large-scale experiment will be successful just after seeing the first 1% of training, or just after seeing the smaller scale version of this experiment, and so on. Moreover, beyond really good intuitions about research directions, as Jason Wei has noted, there are incredible returns to having great intuitions on the dozens of hyperparameters and details of an experiment. Jason calls this availability to get things right on the first try based on intuition YOLO ones. Jason says, YOLO runs. Jason says, what I do know is that the people who can do this are surely 10 to 100 times AI researchers. So the people who can do that are 10 to 100 times better than the best AI, than the average researcher. Yeah, and that makes sense. Yeah, okay. So compute bottlenecks will mean a million times more researchers won't translate into a million times faster research. Thus, not an overnight intelligence explosion. But the automated AI researchers will have extraordinary advantages over human researchers. And so, it seems hard to imagine that they couldn't also find a way to use the compute at least 10 times more efficiently / effectively, and so 10 times the pace of algorithmic progress seems imminently plausible. I'll take a moment here to acknowledge perhaps the most compelling formulation of the counter-argument I've heard by my friend James Bradbury. If more ML research effort would be so dramatically would so dramatically accelerate progress, why doesn't the current academic ML research community, numbering at least in the tens of thousands, contribute more to frontier lab progress? Currently, it seems like lab internal teams of perhaps 1,000 in total across labs shoulder most of the load for frontier algorithmic progress. His argument is that the reason is that algorithmic progress is compute bottlenecked. The academics just don't have enough compute. Some responses. Quality adjusted. I think academics are probably more in the thousands, not tens of thousands, looking only at the top universities. This probably isn't substantially more than the labs combined, and it's way less than the hundreds of millions of researchers we'd get from automated AI research. Academics work on the wrong things. Up until very recently, perhaps still today, the vast majority of the academic machine learning community wasn't even working on large language models. In terms of strong academics in academia working on large language models, it might be meaningfully fewer than researchers at labs combined. And I feel like computer vision, I feel like what they've been working on instead is a lot of self-driving car stuff. So yeah, that could be significant. Even when the academics do work on things like LLM pre-training, they simply don't have access to the state-of-the-art, the large accumulated body of knowledge of tons of details on frontier model training inside labs. They don't know what problems are actually relevant or can only contribute one-off results that nobody can really do anything with because their baselines were badly tuned. So nobody knows if their thing is actually an improvement. Yeah, so you might accidentally research and discover something that has already been discovered. And when instead you could have been making real progress. Academics are way worse than automated AI researchers. They can't work at 10x or 100x human speed. They can't read and internalize every machine learning paper ever written. They can't spend a decade checking every line of code, replicate themselves to avoid onboarding bottlenecks, etc. Another countervailing example to the academics' argument, GDM is rumored to have way more experiment compute than OpenAI. And yet it doesn't seem like GDM is massively outpacing OpenAI in terms of algorithmic progress. That's a good point. You really don't need the most powerful lab you can get. You need the lab that is most hyper optimized to making progress, whether that means it's powerful or not. In general, I expect automated researchers will have a different style of research that plays to their strengths and aims to mitigate the compute bottleneck. I think it's reasonable to be uncertain how this plays out, but it's unreasonable to be confident it won't be doable for the models to get around the compute bottleneck just because it's hard for humans to do so. For example, they could just spend a lot of effort early on building up a basic science of how to predict large-scale results from smaller-scale experiments. And I expect there's a lot that they could do that humans can't do. For example, maybe things more like predicting if this large-scale experiment will be successful just after seeing the first 1% of training. This seems pretty doable if you're a super strong automated researcher with very superhuman intuitions, and this can save you a ton of compute. When I imagine AI systems automating AI research, I see them as compute bottlenecked, but making up for it in a large part by thinking, for example, 1,000 times more and faster than humans would, and thinking at a higher level of quality than humans. For example, because of the superhuman ML intuitions from being trained to predict the result of millions of experiments. Unless they're just much worse at thinking than engineering. So thinking and engineering, I guess, are two different things. Which I mean they are. One's paper and pencil, the other one's actually bringing it to life. I feel like this can make up for a lot, and this would be qualitatively different from academics. In addition to experiments compute, there's the additional bottleneck of eventually needing to run a big training run, something which currently takes months. But you can probably economize on those, doing only a handful during the year of intelligence explosion, taking bigger orders of magnitude leaps for each than labs currently do. Or you could spend one out of the 5 OOMs of compute efficiency wins to do a training run in days rather than months. So that was actually a pretty good analogy I made, where a chemical reaction takes 100 hours because training runs, you have to train the AI, and that is something that's a bottleneck. That's a big bottleneck. All right, so note, while I think this is likely, it's kind of scary. It means that rather than a fairly continuous series of big models, each somewhat better than the previous generation, downstream model intelligence might be more discrete/discontinuous. Okay, that's interesting. We might only do one or a couple of big runs during the intelligence explosion, banking multiple orders of magnitude of algorithmic breakthroughs found at smaller scale for each. So this is complementarities. So complementarities are like where it intertwines with humans. So like with ChatGPT, you have to prompt the ChatGPT. You have to actually read, interpret, and do the things it's suggesting. So that's a big bottleneck if you just never use the AI to accomplish things, or the fact that it would require a human, a complementarity with a human is a huge that's going to slow it down quite a bit. So complementarities and long tails to 100% automation, optional and more depth. The classic economist objection to AI automation speeding up economic growth is that different tasks are complementary. So, for example, automating 80% of what labor humans did in 1800 didn't lead to a growth explosion or mass unemployment. But the remaining 20% became what all humans did and remained the bottleneck. See an example model. A model of this here. I think the economist's model here is correct, but a key point is that I'm only talking about one currently small part of the economy rather than the economy as a whole. People may well still be getting haircuts normally during this time. Robotics might not yet be worked out. AIs for every domain might not be worked out yet, and societal rollout might not be worked out, etc. But they will be able to do AI research. As discussed in the previous piece, I think the current course of AI progress is taking us to essentially drop in remote workers as intelligent as the smartest humans. As discussed in this piece, the job of an AI researcher seems totally within the scope of what could be fully automated. Now, one thing I want to say about barbers still doing haircuts is like, yeah, you can still go to a barbershop and get a haircut, but one thing you can do that I don't think you could do as well back in like the 1800s is you can do it yourself at home. Before, there was that straight edge razor. You had to maintain the razor, clean it up a certain way, whatever. And now we have these like shaving. Just about everyone shaves at home. Nobody goes into a barber to get shaved, pretty much. So, it didn't used to be like that. I don't know. I don't know what I'm talking about. All right, continuing on. Still in practice, I do expect somewhat of a long tail to get to truly 100% automation, even for the job of an AI researcher slash engineer. For example, we might first get systems that function almost as an engineer replacement, but still need some amount of human supervision. In particular, I expect the level of AI capabilities to be somewhat uneven and peaky across domains. It might be a better coder than the best engineers while still having blind spots in some subset of tasks or skills. By the time it's human level at whatever it's worst at, it'll already be substantially superhuman at easier domains to train, like coding. This is part of why I think they'll be able to use the compute more effectively than human researchers. By the time of 100% automation, the intelligence explosion starting, they'll already have huge advantages over humans in some domains. This will also have important implications for super alignment down the line, since it means that we'll have to align systems that are meaningfully superhuman in many domains in order to align even the first automated AI researchers. But I wouldn't expect that phase to last more than a few years, given the pace of AI progress. I think it would likely just be a matter of some additional unhobbling, removing some obvious limitation of the models that prevented it from doing the last mile, or another generation of models to get all the way. Overall, this might soften takeoff some, rather that 2027 AGI to 2028 superintelligence. It might look more like 2026 to 2027 proto-automated engineer, which we kind of have with that Devon experiment. But blind spots in other areas speeds up work by 1.5 to 2 times already. Progress begins gradually accelerating. 2027 through 2028, proto-automated researchers can automate greater than 90%. Some remaining human bottlenecks and hiccups in coordinating a giant organization of automated researchers to be worked out, but this already speeds up progress by more than 3 times. This quickly does the remaining necessary unhobbling, takes us the remainder of the way to 100% automation. 2028 through 29, more than 10 times the pace of progress, and that leads to super intelligence. That's still very fast. So I guess this is still where I'm lost, because as I've said before, I don't understand how making a car, if it's not super intelligence now, why will making whatever it is besides being a super intelligence, why will improving that make it a super intelligence? For example, if you make a car faster, if you give it a better driver, if you put it on better roads, it's not going to turn into an airplane. So I don't understand how more research into the trend lines that we're seeing making GPT better will make it an AGI or an ASI when it is not already in some way. I mean, maybe it already is in some way. I guess you can think of that as GPT-2 to GPT-4. So GPT-2 was capable of what we get with GPT-4. It just wasn't powerful enough. So I think that's probably the answer. Is it is an AGI. It's just an underpowered, underdeveloped AGI right now. So it doesn't act like an AGI. So that's kind of what's meant by achieving AGI, achieving ASI, is getting it to act the way it's already capable of acting. Okay, so the next section is fundamental limits to algorithmic progress, and I think that's got to be it. I just don't have it in me to do a full hour, so stay tuned for the next video. Uh, yep, where we read about fundamental limits to algorithmic progress, optional in more depth. So thanks for watching, and see you in the next one.